Hello, Wharton Warriors. This is part two of our series on data science interview questions. Today, we'll touch questions on statistics. I'll show you three technical interview questions from Google, Facebook, and Two Sigma. Take a moment to solve these three problems, and I'll walk you through step by step. Okay, so the first question, assume you are drawing an infinite set of independent IID random variables that are uniformly distributed from 0 to 1. You keep drawing as long as the sequence you are getting is monotonically increasing. What is the expected length of the sequence you draw? Okay, to solve this problem, you need to understand the concept of the expected value and the definition of E. First of all, let me touch the definition of E. As you probably remember, E as a series, 1 over 0 factorial plus 1 over 1 factorial, 1 over 2 factorial, and keep goes on and on, right? So this series converges to the value of E closely tied to the process that involve exponential growth or decay, right? So let's address the problem at hand. We need to determine the expected length of sequence IID random variables drawn from a uniform distribution. So let xi be the indicator variable where xi equals 1 is the sequence remains increasing up to the ith element. So sequence increasing up to nth, I'll say ith moment, ith element, and xi 0 otherwise. So the expected length of the sequence can be expressed as the sum of expected values of these indicator variables. So the expected value of x1, x2, x3, this keeps goes on and on. When x equals 1, the sequence increasing up to one element is just 1, right? And 1, and then as it grows, it will keep decrease, plus 2, 1 over 3, and so on and on. So this sum represents the harmonic series, which is related to the natural logarithm function. But we know that E starts from 1 plus this. So simply subtracting minus 1 from E makes equal to this harmonic series. So the next question is about two games involving dice that you can play. In the first game, you roll two dice at once and receive a dollar amount of equal to the product of rolls. And in the second game, you roll one die and get the dollar equivalent to the square of that value. First game is equivalent to the product of the rolls, and second one equivalent to the square of that value, which has the higher expected value and why. So this problem involves around calculating expected values for two different random variables. And the expected value, let's denote the average outcome if an experiment is repeated many times. So let's define game one. What is game one? You roll two dice. The dollar amount you receive is the product of the numbers rolled. So let's denote this by x1 multiplied by x2, okay? So where x1 and x2 are the outcomes of two dice, okay? So x1, since x1 and x2 are independent, right? They're not dependent on each other. So the expected of the product is simply expected value of x1 multiplied by x2. So this is exactly as, since we know that these two are independent, you can split this expected value of x1 and expected value of x2, okay? And for a single die, the expected value is the average of all the possible outcomes. So in simple fair dice, the expected value of simple fair dice is 3.5. So the x1 multiplied by x2 is, oops, I wrote it again. This is actually 3.5 multiplied by 3.5, okay, which is 12 plus 2.5. And for game two, it says we get the dollar amount equivalent to the square of that value, okay? So where is the square of this value is x squared, right? This is calculated by finding the average of the squares of all the possible outcomes. So this is exactly as, we're going to square all the possible values here, divided by 6, which is about 91 over 6, which is about 15 something, right? So let's compare these two values. So we notice that game two has the higher. So game two has a higher expected value than game one. So meaning the second game, where the dollar amount is the square of the roll, has a higher expected value, right? So this is game 2 because we have a higher expected value. And this last question, let's read it together. Say we have two random variables, x and y. What does it mean for x and y to be independent? What about uncorrelated? So we have to know the definitions of independent and uncorrelated. We have to define this. What is the condition for independence? So we have two random variables, x and y. So the probability of x and y happening at the same time. Normally, so this is a joint probability. Takes the value of x, the big Y takes the value of small y. It's the probability that the both events occur simultaneously. But in general case, this cannot be factored unless x and y are independent. So given that x, y are independent, so let's define it here. When x and y are independent. When x and y are independent, we can split this. The probability of big X equal to x and multiply by the probability of big Y equal to y, right? For all x and y, right? So this means that the joint probability of x and y happening together is just simply the product of their two individual probabilities, okay? And independence implies that knowing the outcome of x gives no information about the y because they are completely independent, right? They're not dependent on each other. So let's talk about when x, y are uncorrelated. If two random variables x and y aren't correlated, if and only if their covariance is 0. What is covariance? Covariance of xy is expected value of xy minus expected value of x minus expected value of y. This is how we get covariance of xy. So if the covariance is 0, meaning that there is no linear relationship between x and y. So it does not necessarily mean that they're independent. Uncorrelation only implies the absence of linear dependency, not the absence of all types of dependency. Okay, so only linear independency. No, okay, I'll say no linear independency. Linear dependency. To illustrate this difference, I'll make this example. So example here, let x be the random variable that takes on values -1, 0, and 1 equal probability. Let's define y equals 1 if x equals 0 and y equals 0 otherwise. Okay, so this is the condition. Here, what is expected value of x? Expected value of x is just the average of all the possible outcomes. So this is automatically 0. What is expected value of y? We just take the average of all possible values, which is 1/3 multiplied by 1 plus 2/3 multiplied by 0. So this is 1/3. And what is their covariance? Covariance of x and y, expected value of xy minus expected value of x multiplied by expected value of y. So what is expected value of x and y? Well, we have to find a situation that x, y are uncorrelated. So this is automatically 0. This one is automatically 0. And we know that expected value of x is 0 and multiplied by the expected value of y, which is 1/3. And this is indeed 0. So this is the situation that x and y are uncorrelated and this is the situation. And so since the variable x and y are uncorrelated because their covariance is 0, however, they are not independent because the value of y depends entirely on x, right? So we just made the situation that y depending entirely on the value of x. So this example shows the distinction between independence and being uncorrelated. You can still have uncorrelated values that do not show a linear relationship, but they still might be dependent on each other. So thanks for watching this video. And if you have any questions, please leave them on the comment. All right. Thank you. Bye.